Hello everyone, in this video we're going to be talking about searching and sorting. You'd be familiar with these terms in everyday life, like searching for your keys or maybe sorting objects in relation to their height or something like that. But in computer science and in this course we're going to be looking at searching and sorting in a little bit differently. So it's still the same ideas, but what we'll be mainly dealing with will be numbers. So we'll be searching and sorting through different numbers. And the reason why we use searching and sorting is to help us make useful websites. For example, you're all probably familiar with Facebook. When you log on to Facebook and you see your timeline, the most recent stories are usually at the top. And then as you scroll down, you see later stories. So you could say these list of stories, or I think Facebook refers to them as posts. They're in order, starting with the most recent post and then continuing down to the latest post. So let's get back to a more practical example. So let's imagine we have a box here. And in our box we have a set of numbers. Let's say we have 2, maybe we have 15, then we have 6 and 3 and 12 and we'll say 5 and 9. So this is our numbers. You can see that we have 7 numbers in our box. Now we want to perform a search. Okay, so we want to search for one of the numbers. We want to search for the number 3. So as humans, we can look at all these elements and then pick out the number 3. But unfortunately for computers, it doesn't work like this. And rather than having these numbers in a box, as I called it, we usually have these set of numbers in a data structure called an array. So it would look something like this. We'd say 2, 15, 6, 3, 12, 5, and 9. And I'm just going to put square brackets around all of our numbers. And now if we want to go and look for that same number, 6, if we were a computer, we would have to do this by performing some set of rules. And one of these rules, and the most simplest rule, would be to start at the first element, or the first number, and check to see if that number that we're looking at, which is 2, is it the same as the number that we're looking for? So the number we're looking for is 6. So 2 is not equal to 6. So then we'd go and we'd move on to the next number in our array. And we'd check to see if this number, which is 15, we'd check to see if it is equal to 6. Again, it's not equal to 6. So we'd move on to the next number. And then we get to 6. And 6 is indeed equal to 6. So it's perfect. So we could say that this array has got the number 6 in it. So we could say 6 is true. Now imagine we got a number like maybe 25. We'd have to do the same thing. We'd go to the first number, check to see is it equal to 25. It wouldn't be. So we'd go to the second one. It also wouldn't. Third, fourth, fifth, sixth. And you see what I'm getting at here. We'd have to go through the whole entire array just to find out and just to say that 25 is false because 25 is not in the array. Now this video is just an introduction, so I'm not going to get into it in too much detail, but there's 2 types of searching, and the first type is called linear search, and that's basically what we're after doing here, but I have a follow-up video where we go through linear search in more detail. So if you didn't quite understand it, don't worry about it, and there's other more complex situations that we have to think about when we're doing linear search. For example, there may be duplicate values, so there could be more than one 6 in the array, and if there is, what do we do in that scenario, and so on. The second type of searching we can do in our array is called a binary search, and a binary search is much faster, and we'll get into a discussion on what faster means in a different video about complexity analysis. But it's basically a better type of searching that we can do on our array, which allows us to find the element faster. But there's some certain prerequisites for that array. For example, if we want to do binary search on an array, the array must be sorted before we can implement our binary search. Otherwise, we're not actually going to find the right answer at all. And we'll get into examples of binary search in future videos. So now I'm going to move on to an introduction in sorting. And as you can see, I'm going to use the exact same numbers as I did for searching. So we've got our numbers here, which you can imagine as a box or something like that. And then when we transfer our numbers into a computer readable format, which is an array in this case, there's other different data structures you can put your numbers into. But an array is one of the more simpler ones that we can use, because an array is just a list of numbers. So after 2 we have 15, after 15 we have 6, so it's quite easy to understand the progression of the numbers, unlike some of the other data structures which mix the numbers up a little bit more. Okay, so let's talk about sorting. So imagine we've got our array here and we want to go and sort these elements. As a human, you just look at this and you'd see, okay, so 2 is first, then you'd look and you'd see, okay, there's 3, then there's 5, 6, and then there's 9, 12, and 15. And that's how you would sort them, and you'd write them out, as I've said. But as a computer, again, you need to follow a certain set of instructions. So we need to go and look at all these elements. So for example, one approach might be to go and look at 2, and then we assume 2 is the smallest number, but we're not sure, so we have to go and look at all the other elements in the array. And if all the other elements in the array are smaller, we then can add 2, or we can say 2 is going to be the first element because it's the smallest. Then when we move on to our second element, which is 15, again, we presume that 15 is the smallest element. Now, it's not actually the smallest element, and we'll get to that in a minute. And then we'll compare it with 6. And then we can see that 6 is actually smaller than 15. So we would then replace this 15 with a 6. And then we'd continue with our 6, and we'd loop through the array and see is there any other smaller elements. And then we get to 3, and then we see that 3 is indeed smaller than 6. So we would swap 3 with 6. So now we would say 3 is the smallest element, not including what we've already defined is the smallest, so 2. So then we'd move on and we'd say, okay, we've got 3 as our next smallest element. Is 3 smaller than 12? It is. Is 3 smaller than 5? It is. Is 3 smaller than 9? It is. Brilliant. And then we'd move on to our next element here, which is 6. But if you remember, we actually switched 6 from last time, so we would actually have a 15 in the place of a 6 here. And then you compare 15 with the next element, and again, this would no longer be 3 because 3 is already switched, so you'd be comparing 15 with 6, and then you would find out that 6 is smaller, and then you go through it again and again. Now, I don't want you to worry too much. I'm not going to go into too much detail, and if you didn't quite get that explanation, that's fine. This is only an introduction. But I just want to mention that there's 3 different types of sorting that we're going to learn. So the first type of sorting that we're going to learn about, and we're going to have a dedicated video on each of these 3 different types of sorting algorithms. Our first one we cover will be bubble sort. The second type of sorting algorithm that we're going to cover will be insertion sort. And the final sorting algorithm that we'll cover will be quicksort. Now, quicksort is actually the best type of sorting algorithm, and what I mean by the best type is its speed is faster, so it's complexity analysis. And again, if you don't know what complexity analysis is, don't worry about it. There's going to be a separate course on the complexity analysis of each individual algorithm that we're going to be going through, both for searching and sorting. Hello everyone, in this video we're going to talk about searching, and we're going to talk about linear search. Linear search is going to be one of the first 2 searching methods or algorithms that we're going to cover in this course. We're going to start off by having a number of elements or a number of numbers, and then we're going to perform some searching operations on those list of numbers. So let's start off by picking some random numbers. I'm just going to write some numbers down here. I'm going to pick 5, 81, 2, 9, 8, 15 and 6. So these are the numbers that we're going to work with today. We can see that we have 7 different numbers, and the first task that we have today is we want to check for a number. So the number that we want to check for is the number 8, and we want to see if it's actually in this array of numbers. So with linear search, we have to start from the beginning. So the beginning of our array is at 5, and we're going to check to see if 8 is equal to 5. Now, obviously by checking this, we can see that 8 is not equal to 5, so we move on to our next element. And our next element is 81. And we can also see that 81 is not equivalent to 8, so we move on again to number 2. And we can see 2 is not equal to 8, and then we move on to 9. We can see 9 is also not equal to 8. And then we finally get to 8 here, and we see that 8 is indeed equal to 8. So then we can say that this is true. This statement is true because we've found this number that we're looking for, which is 8, in our numbers array. Now let's imagine that we have the number 30. And with our number 30, we want to go and check our array. But we have to do the exact same thing, only we're not going to come to a solution because we can see by looking at this here that the number 30 does not exist. But we go to 5, we see that 5 is not equal to 30. Same for 81, same for 2, same for 9, same for 8, 15 and 6. And then once we've got to the end of the array, there's no point in looking anywhere else because we can't. So we then set this to false. Now the next problem that we might have is, what if we're looking for the number 8, right? And then we not only want to find out where the number 8 is, but we want to find out where it's positioned in our array. An array is numbered from 0 to n minus 1. So for example, this first element will be 0, then our second element will be 1, our third element will be 2, this will be 3, 4, 5 and 6. And if you remember what I said that there's 7 elements in the array, so we refer to this 7 number, or however many elements is in our array, so we define this as n. So for this array, n is equal to 7 because there's 7 different numbers in it. So if we look at this here and we see that it ranges from 0 to n minus 1, we know that n is 7 minus 1, that means it's 6. That means that our range is from 0 to 6, and that's what we have in here. So I just wanted to clear that up before I dive in any deeper. So now that we know what these indexes are, we want to return the index of the number that we're looking for. So in this scenario, again, we're looking for the number 8, and we want to return wherever it's found. So for example, we can see that this number 8 here is found at index 1, and it's also found at index 4. So rather than setting a boolean like a true or a false to the number 8, we want to set the number where it's positioned. So for example, we would check the first element, see if it's 8, it's not. Then we'd go and check the second element, it is. So we want to have 1 here. But then we also want to go and check through the rest of the array, because just because we found 8 in this solution here, we get a true back, but that doesn't necessarily mean that there's only one value in the array. As you can see in this example, there's 2 values. So we'd have to go to our third element and check to see is 8 8. It's not, so we check our next element and our next one. And now we found a second element, and now we know that it's found at position 1 and position 4. Even though that we found 2 elements of the number 8, we need to keep checking, okay? So we need to check this 15 and we need to check this 6 just to make sure that there's not a third element equal to the number 8 in our array. And that's how linear search works. We start at the beginning and we loop through, or we go through every single number until we get to the end. And when we talk about complexity analysis, we usually talk about big O, and we'd say that the big O of this would be n, because n is the number of elements that's in our array. So as I remember before, our n is 7, and we needed to perform 7 different checks, because we checked this. We checked every single element in the array. So that's why we say it's big O of n. Now, if you're confused by this O, I would suggest you to look at our complexity analysis videos. Hello everyone, in this video we're going to talk about searching, and we're going to talk about binary searching in this video. So if you've seen our previous video on searching, we talked about linear search, and if you haven't looked at that, I would suggest to look at that one first, because that's a little bit more simple and straightforward. This is a little bit more advanced as far as searching goes, but let's go into it. So we've got a different data set here this time. We're using 7 different elements, similar to our previous video, but you'll notice there are different numbers to start with, and you might also notice that there's a pattern. So you can see 3, 5, 8, 12, 20, 25 and 30. They're all going up. So they're going up in ascending order, and we could say that all these list of elements, or this array of numbers, is sorted, which it is, and that's a prerequisite for binary search, or it has to be something that's performed before we can actually do a binary search. If we had the list of elements that we had in our previous video for linear search, we wouldn't actually be able to perform this operation, because we just wouldn't be able to get our desired answer, because this is not the way binary search works. So let's go and pick a number, like let's say the number 25, and we know that 25 is in this array, so we want to find out if it's true or false. So by looking at this, we can go and look at the middle point. So the middle point in this would be the number 12, because there's 3 this side and there's 3 this side. Now there could be 50 one side and there could be 50 the other side, but we pick our number in the middle, roughly. If it's an even number, there's obviously going to be slightly more numbers on the right or the left, or slightly more numbers on the left than the right. But in most cases, we get the middle number, and we check to see if this middle number, which is 12, we want to check to see is it bigger or smaller than our number that we're looking for. So we know the number 12 is smaller than the number we're looking for. So since this is ordered, we can basically rule out everything to the left of 12, including the number 12 itself. And we know that our answer, if it exists, is somewhere over here in these 3 blocks. And once we get to these 3 blocks, we then change the number we're looking at to the middle of these 3 blocks. So we change this to the number 25. And now we go and we check to see, is 25 equal to this number? And it is. So we can say this is true. Now, this is actually much faster than linear search, and this is why if you want your algorithm to perform in a relatively quick time, you would want to perform binary search rather than linear search. Now, as you can guess, it's not always possible. Your elements won't always be sorted. So let's move on to our next example, which would be to look for the number 2, let's say. And we want to see does 2 exist in this array. So I'm just going to get rid of these arrows and lines, and we're going to do the exact same thing that we done last time. So we're going to look at 12, because 12 is our middle number, and we want to see if our number that we're looking for, which is 2, we want to see is that lower or greater than the number 12. And we also want to check to see is it equal, because if it's equal, then we've found our solution. But in this case, it's not equal and it's not higher, it's lower. So we know that if our element exists, that it exists in one of these 3 different numbers. And then we go to the number 5 here, because we've got 3 numbers, so we pick the middle number, which is 5, and we check to see if 2 is equal, it's not, if it's greater than, it's not, or if it's less than 5. And in this example, 2, our given number, is less than 5. So we can then rule out all numbers to the right of 5, which in this case is only one number, it's only 8. And we can also rule out the number 5 itself. So now we're only left with one element. And since we're only left with one element, we only need to check if it's equal. So it's not actually equal to our number that we're looking for, which is 2. So we would then return false. Now, if this was a longer array and there was more numbers to the left of 3, we would say, okay, it's not 3, it's less than 3, so it's to the left. But since there's nothing to the left of 3, we would then return false, meaning that it doesn't exist in our array. Again, similar to our last video, I'm going to go through the complexity analysis of our binary search algorithm. It's big O of log of n. Now, you might be thinking, okay, in our linear search algorithm, we had n. Now, in this one, we have log of n. Does it really matter? It does. It's actually a lot more efficient. And again, I'm going to encourage you to go to our complexity analysis videos if you're unsure of what this log of n means, or you're unsure about big O in general. I'm not going to go into detail in this video because I want this video to just look at searching and binary search. Hello everyone, in this video we're going to talk about bubble sort. Bubble sort is the first sorting algorithm that we're going to talk about. It's not the best one in terms of efficiency, but I think it's a really nice one to start off with. It's really simple to understand. So to start off by sorting some elements, we first of all need a list of elements to sort through. So what we can do is we can just create a random array of numbers. I'm going to create a random array and we're going to go through it using bubble sort, and you'll see how we can bubble up the highest element. It ends up being pushed to the very right of the array, and some people refer to this as bubbling because the highest element or the greatest element is being bubbled up or pushed to the right hand side. So let's start off by creating our array. I'm going to have my first element as 8, then I'm going to have 5, 18, 20, 2 and 9. So this is my array of elements. It's pretty short, there's only 6 elements. I don't want to have this array too long because the procedure itself, bubble sort, can take a little bit longer than some of the other ones. So we start off by looking at the beginning of the array. So we look at the first 2 integers, which is 8 and 5, and we want to check to see are these in the correct position. So basically the smaller elements should be on the left hand side and the bigger elements should be on the right hand side. So by this definition, 5 and 8 are not in the right positions because 8 is greater than 5. So we're going to swap these around. So we're going to swap this 5 with the 8. So 5 will go here and 8 will go here. So now we know in this new array that we've formed, we know that this ordering is correct. Now we need to move on to the rest of the array. So I'm going to just fill the rest of these in to make it a little bit simpler for you. When you're developing your algorithm using pseudocode or real code like JavaScript, you wouldn't actually be creating a new array. This here is just for visual representation to help you understand the process a little bit better. So what we do then is we compare 8 with 18 and we want to check to see is that in the correct order. So basically asking, is 8 less than 18 or is 18 greater than 8? And it is. And now we want to go and check our next 2 elements. So we want to check 18 and 20. And 18 and 20 are actually in the correct position as well. So we can then move on to the next 2 elements, which is 20 and 2. Now unfortunately these 2 elements are not in the correct position, so we're going to have to swap them. So 2 is going to go here and then 20 will be here. And we can imagine all these numbers to the left will be staying the same, so I'm just going to fill them in for clarity. And we've also got a 9 at the end that we must check. So now we want to check our last 2 elements, which is 20 and 9. And again, these are out of order as well, so we're going to need to swap these around. So we're going to have 9 here, and we're going to have 20 here. And I'm going to just, again, fill in all the rest of these so there's no confusion. So now we've actually went through the whole array once. We've compared each individual element with another element. So we can say we've looped through the whole array once, so we could say n times is usually the terminology that we use, and after we've looped through it once, or n times, we are sure that our last element, which is 20 in this case, but whatever our last element will be, depending on our given array input, will be in the correct position. So 20 is in the correct position. Now all the rest of these elements here, they may be in the correct position or they may not be in the correct position, but we know for a fact that 20 is okay. So we only have to look at the rest of the elements in the array to sort these out. So again, we take a similar approach. We compare the first two elements, which is 5 and 8, and we want to check to see are these in the correct position, and they are. And then we go on and we check the next two elements. So we check 8 and 18. These are also in the correct position. And then we go and we check 18 and 2. These are not in the correct position, so we need to swap these around. So 2 becomes here, 18 becomes here, and we'll fill in our 9 and our 8 and our 5 just to be clear. And now we've got this. Okay, we've got 20 here at the end, but we don't really care about 20 because we know it's correct. It's this here that we're concerned about. So we go and we compare 18 to 9, and this is also out of order. So I'm just going to bring this array up here because we're running out of space down here. So we would go and swap these elements. So 9 would come before 18, and again after 18 we have 20, but we don't necessarily care about it because we know that it's in the correct position. And then we have 2, 8 and 5 before this. So this is our new array here that we're looking at, and I'm just going to get rid of this here to create some space for us. So now we've looped through the array once more, so we could say this is our second time looping through the array. So once we've looped through it a second time, we know that the last element is in the correct position and the second last element is in the correct position. Now we just need to worry about these 4 elements. So again, we do the exact same thing again. We compare 5 with 8, this is in the correct position. 8 with 2, this is not in the correct position, so we're going to have to swap these. So 2 becomes here, 8 becomes here, 9, and we just fill in 18 and 20, and 5 at the beginning as well. Now we need to go and compare 8 with 9. We know 8 and 9, they're both in the correct position, and now we can stop our iteration, or our third pass through the array. So now after passing through the array 3 times, we know that the last element is okay, the second last element is okay, and the third last element is okay. These are all ordered. But as far as these 3, we're still not sure yet. So we compare 5 with 2. This is not in the correct order, so we switch them around. So we put in 2 and 5. Then we compare 5 with 8. And we know that 5 and 8 is in the correct order, so I'll not bother writing this bit out. I'll just put 8 down here, and I'll follow it up with 9 and 18 and 20. So after this, we know that 20 is in the correct position, 18 is in the correct position, 9 is in the correct position, and 8 is in the correct position. Now, these 2 elements here, we're not sure of. As we look at it, we know this is in the correct order. But as far as the computer understands, it's not sure. So it wants to go and check these again anyway, because it doesn't know by looking at this array that it's in order. So it goes and checks these 2 first values here, and it sees that they're both okay. So then we know everything to the right of it is okay. So we can now say this array is sorted. And this is what we do to sort our array using bubble sort. Hello everyone, in this video we're going to cover insertion sort. Now in our previous video we covered bubble sort, which is probably the easiest sorting algorithm for us to understand. This one's not that complicated, but in the future we'll be covering quicksort, which is a better algorithm as far as complexity analysis, but it's also probably one of the harder sorting algorithms to understand or reason about. When you think of insertion sort, Imagine an array, and on the left hand side of your array, imagine that you have a partially sorted array, and that partially sorted array on the left hand side is going to grow as you perform your algorithm. So let's jump into an example here. Let's create a random array. So I'm going to just put some elements into this array. I'm going to say we have the numbers 8, 5, 18, 2, and 9. And we want to sort this array using insertion sort. So if we go and look at the very left of our array, so we just look at this single figure or this single number 8, we can actually say that this is sorted. And the reason why we can say that this is sorted is because there's only actually one element that we're looking at. So we know that 8 is sorted. So once we know that this single part of the whole array is sorted, so you can imagine this here as being sorted. I know at the moment it only has one digit, and all the rest of this array is unsorted, or it's potentially unsorted. We haven't checked it yet. We could have an array that's perfectly sorted before we go and perform our sort algorithm, but we don't know this ahead of time. So our next step is to move on to our second digit. So we can see here our second digit is 5. So now we're no longer just looking at 8, but we're looking at 8 and 5. And if we look at 8 and 5, we can check to see if these two numbers are sorted. And they're not, because 8 is greater than 5. So what we want to do is we want to swap these elements. So we want to put 5 here, and we want to have 8 here. And the rest of our array is not going to change. It's just going to be the same way it was before. So it'll have 18, 2, and 9. And I'll just put the square brackets around this to make sure there's no confusion. And now we know that this part of our array is sorted. So our two elements to the left are sorted, but we're still unsure about the rest of our array. So our next step would be to go and check our next element. And our next element is 18. So we want to see, is 18 greater or less than 8? 18 is greater than 8, so this is actually in the right position. And we don't have to compare 18 to 5, because if 18 is greater than the first number that we check here, which is 8, we know that it's going to be greater than all the other elements or all the other numbers to the left of this number, which is 8 in this case. So this is good. We can then move on to our next stage in our algorithm, which is to check our next element to the right. And our next element to the right is 2. So when we compare 2 to 18, we check to see if 2 is greater or less than 18. And we can see that 2 is less than 18. So if 2 is less than 18, we need to swap these elements. So you could imagine our array would look something like this. And I'm just going to draw it out here for you. 5, 8, and now we don't want 18, we want 2. And then we fill in 18, and we finish that off with 9. Now, we haven't fully got a working solution here, or we haven't fully completed this step, because if it's a case that this number here on the right is less than the number on the left, then we switch it. So that's perfect, we've done that. But if we had to switch it, we also need to check this number here that we've just moved and compare it to the element to its left. So in this case, the number 8. So we need to check to see, is 2 greater than 8? And it's not. So it's not in the correct position. So again, we need to swap this again. So we would then have 5, 2, 8, because these two swap. And then we would have 18 and 9. And then imagine if we have 5, 2, 8 here. We also need to check this number 2 with 5, because again, we've just moved this number. So we need to make sure to compare it to every single element once it has been swapped previously. So again, 2 is less than 5. So we're going to have to rewrite our array to look something like this, we're going to have 2 at the start, then we're going to have 5, then we're going to have 8, now we're going to have 18, and now we're going to have 9. And now we go to our next element, which is 9, and this is our last element. So once we've completed this last element, our array should be sorted. So again, we can check this by comparing 18 to 9. 9 is less than 18, so it's going to have to be swapped. So it'll look like this, 9 and 18. And what we can do now is we can compare 9 to our next number to our left, which is 8. And if our number here, so if 9 is greater than 8, everything's okay, and we can just fill in the rest of the array the way it is. Now, if this number here wasn't 9, let's say this number was 7, which is less than 8, we would then swap 7 with 8, and then we would have to compare 7 just to check to make sure it's in the right position with the number 5 here. But in this example, 9 is greater than 8, so we can just fill in the rest of the array the way it is. And if we just fill in 8, 5, and 2, and we'll wrap that in square brackets to identify it as being an array. And now if we go through all our elements, 2, 5, 8, 9, and 18, we can see that this is now a sorted array. So if you want to know more about the complexity analysis of insertion sort, or you want to know how you'd go about coding up a solution to implement insertion sort, go and check out some of our complexity analysis videos. Hello everyone, in this video we're going to go through quicksort. Quicksort is the third sorting algorithm that we cover here, and it's the best algorithm, or the quickest algorithm, hence the name. But the problem with quicksort is that it's a little bit more complicated to understand or reason about when we try and implement it in our programs. So for example, if you had to code a solution in bubble sort or even insertion sort, it would be much easier to create the code, while in quicksort it's much more difficult. And one of the main reasons for this is because quicksort is called a recursive algorithm. And if you don't know, a recursive algorithm is an algorithm or a function that calls itself within the function. So it means from a complexity point of view, it's very time efficient as far as the computer is concerned, but it's not as easy for us to understand as humans. So I'm going to create an example and we're going to jump into it. So for this example, I'm just going to pick the numbers 8, 5, 18, 20, 2, and 9. So this is the array that we're going to work with. This is the array that we want to sort. So the first thing we need to do is pick a pivot. So the idea of a pivot in quicksort is it's just a number, but that number will be our pivot or our midpoint value, and all the elements to the right of our pivot will be greater, and all the pivots to the left of that number will be smaller. So for example, if we picked a number like 9, we would go through all these elements here in the array and we would put them all either to the left or to the right of 9, depending on what number they are. Now, you might think, how do you pick the pivot? And it doesn't really matter to a certain extent on what number you pick as the pivot. You could pick like the number 18, but in most cases, for simplicity, we usually choose our pivot being either the first number or the last number. So you can do either or. Now in this example, we're going to continue with selecting the last number, which is 9. So when you've got your array, pick your pivot, let's say 9, and we're going to put 9 down here. We're going to put a little box around it because we know this now is our pivot that we have selected. And now we need to go through the rest of the array. So we need to go and look at 8. Now we can see that 8 is smaller than 9. So we select our first number, which is 8. 8 is less than 9. So we would put it on the left hand side, which is here. Then we'd move on to 5. 5 is also less than 9, so we would put it on the left hand side also. Then we come to 18. Now 18 is greater than 9, so it would go on the right hand side. So we put 18 here. Then we move on to the number 20. 20 again is bigger than 9, so it would go on the right hand side. And then finally we've got the number 2. So 2 is obviously smaller than 9, so it will go here on the left hand side. Now by looking at this you might think this isn't sorted, which it's not, but part of this array is sorted. So for example, the number we picked, which is 9 being our pivot, everything to the right of 9 is correct. Everything to the right of 9 is bigger than 9. And you can see this by the numbers 18 and 20. Now, these numbers might be, mixed up. It just so happens that these are in the correct order. When we look at the left-hand side, we can see that all these numbers here are also correct in terms of they're all less than our pivot, which is 9. But if you look closely at them, you can see that they're not ordered. And in fact, they're actually totally unordered. They should be the other way around. But you can see with this example that all the numbers on the left are indeed less than 9, but there's no guarantee that they're sorted or that they're in order. So we need to go through another iteration of this algorithm. And next we pick 2 more pivots. And again, we're going to keep going with the standard of taking our last elements. So you could imagine these numbers here as being their own separate array, and you could imagine these 2 numbers here as being in their own separate array. So we're going to pick the last number for each. So 20 will be our pivot in this case, and we can put a box around it. And 2 is going to be our pivot in this case, and we can put a box around 2. Now we need to go and iterate through our subarrays. So we can see by looking at this, we know that 8 is greater than 2. So 8 would go here. And we know that 5 is also greater than 2. So 5 would go here. Now for 18, we know that this is less than 20. So we would put it in here. Now again, you can see if we look at this array, it's sorted in terms of our number that we've picked, our pivot, which is 20. The numbers to the left and to the right of this are correct. Now there's no numbers to the right of this pivot, but there is one number to the left and it's in order. Now it was in order before, but now we definitely know that it's in order. Now if we move on to our next array here, we can see our 3 elements and our pivot here is 2, and the 2 numbers, both 8 and 5, are correct as far as saying that they're in the right position because they're to the right of the number 2. But again, these numbers themselves are not sorted, and we need to keep going down layer by layer until we only have one element left. So for example, here on the right hand side you can see that there was only one element here, which was 18. So we know that this part of the array here, we could say that this part here is sorted. This gets a tick. But this one here is still unsure. Now this could be sorted, but we don't know fully yet, and we won't know until we get to only one single element. So we're going to continue with this then by picking our pivot. So our pivot is just going to be between 5 and 8, so our pivot will be 5 here, and then we go and check to see our number. Again, this is our last number, so once we've done this, we know that the array is sorted. So we look at this and we see, yeah, okay, 8 is greater than 5, so 8 would go to the right, and we can just bring all this stuff down here just to check our answers. So we bring down 18 and we bring down 20. So do you remember that I said this was a recursive algorithm? So meaning the function calls itself. So with this, there's a function call at each of these layers. And I'm going to just split these up into layers to allow you to visualize the problem a little bit better. So you can imagine this here as our first layer. So we'll call this number 1. And in this first layer, we picked our pivot as 9, and we placed our elements to the right and left depending on what number they were. Now in this here, you can imagine this as our second step. So in our second step, we were splitting our array again, but in this case, we had 2 different pivots, and these 2 different pivots dealt with 2 different subarrays of numbers. And then finally, our third function call here, we only had to pick 1 pivot for this, which was 5, and then we put 8 to the right of that. I will just fill that in. So now that we've performed 3 different steps, you can think of it as us going 3 layers deep. So when we go 3 layers deep, we have to go back up. So when we go back up the layers, we know for sure that whatever order we have our elements in, they will be sorted. So for example, when I take 5 as my pivot and I bring this up here, I know that this is sorted. So I would get a result like this, 5 and 8, and that's what I would pass up. And once I've passed this, we can forget about this layer and we only want to focus on these 2. So on this one, we seen that 2 was our pivot and everything to the right of that was bigger. So we know that 2 goes here. And then we also have our second pivot here, which is 20. So 20 will go here. And then we know that 18 is to the left of it. So we place 18 here. And now we can put an X here because we've completed our work here. And now we're going to go to the first call that we made. And that just deals with our pivot of 9. And we remember that 9, everything to the left and to the right of it. So we put 9 in the middle here. And now if we go and check this, we can see that it goes from 2, 5, 8, 9, 18, 20. And this array is now sorted. Now, as I said at the beginning of the video, this is a little bit more complicated than insertion sort and bubble sort, but it's much more efficient. And if you want to find out more about how efficient it is or how efficiency and complexity work, I'd suggest to check out our complexity analysis videos.